All right, picking up the second half of the Sun Notes, Flip Notes Part 2. I'm out in the front porch, so the car's driving by already. Ignore the background noises. So remember, sunspots do occur in magnetic poles, north and south magnetic poles. And here's where we left off. The rotation is not the same. It's a gas. And like I said, when you put a lot of fluid in a blender, like making a milkshake, it spins faster right where the propellers are spinning. Propeller in the sun, of course, is its core. So when the core is spinning, it's going to move the gases in the middle a lot faster. They take 25 days to rotate, make a complete 360 around the sun, whereas the poles go slower. They take 27 days. So kind of like a blender, you see the top spinning slowly, but the middle's zipping around 1,000 miles an hour. Same thing with the sun. It takes 2 days faster to spin at the equator. Sunspots do vary from appearing for a whole lot to virtually none for a period of time. That's called the Maunder maximum, Maunder minimum. It's an 11-year cycle. So you get your Maunder max, and then in that 11-year cycle, it goes way down to a minimum, what's called a Maunder minimum. So back in March of 2001, you had a whole lot of sunspots, big ones. Then 11 years later, not much. Goes through a cycle. So the solar winds, the fifth or the seventh and final, what I call layer of the sun, is the solar winds, and they push out tremendously past the sun. You can see this nice diagram of how our Earth's magnetosphere protects us from the solar winds. They put up a magnetic protection. And at the poles, you can see it dips down at the poles, so some of the solar winds do come down to the poles. When they come down there, they interact with some of the ions up in the ionosphere and charge those up to make lights we call the aurora. So solar winds are a constant stream of electrically charged particles flowing from the sun. From the corona of the sun, to be more exact. And the aurora, here's a nice view from the space station showing A, the Earth is round, B, that aurora are lights occurring way up in the ionosphere, way up high in our atmosphere, where they're being the sun's, the corona's electrically charged particles, the solar winds, are exciting and lighting up those molecules way up there. So you get the cool green colors, and everything else. Again, caused by the solar winds penetrating the Earth's magnetic field at the poles and lighting up ions in the atmosphere. You get a really strong burst of solar winds. I'll push far enough towards the equator that you can hit up in Canada. They have had several since I've been teaching here at Lindbergh that we've been able to spot from Missouri. However, every time that happens, we happen to have so much cloud cover you couldn't see diddly squat. Nice picture, some canned picture of aurora happening up in Alaska. They threw some lights inside of an igloo to make it look real cool in front, so it's art, but it's really cool. The aurora borealis is the name of the auroras that occur in our northern hemisphere. The ones that occur in the northern lights. The ones that occur down south over Australia and the southern hemisphere are termed aurora australis. Same phenomenon, just different names for different hemispheres, different sides of the earth. The southern lights. And there's a big coronal, what they call a CME, a coronal mass ejection, where you get a huge burst of solar winds from the corona of the sun. And this happened to be, man, it's hard to see the date on that. It's so pixelated because I blew it up. But a coronal hole from the coronal mass ejection, and that's what causes power outages up north. It causes a lot of huge aurora. There we go. There's a picture of a little solar flare shooting up in the approximate size of Earth. So you can put a lot of Earths underneath a solar flare. Boom. Boom, baby. Used to be a lab I do called Hands-on Universe, which I got from University of California, Berkeley. And we could do this on computers and we measure. We'd actually take a picture of the sun. We'd find a solar flare, then we'd find out how many Earths could fit under that solar flare. Great program. Unfortunately, it can't readily be loaded up on our Chromebooks, so I haven't been doing it the last 2 years. And this year, I was going to try it again, but yeah. Magnetic storms occur when solar winds, the plasma from the coronal holes, adds an extra punch to the normal solar winds, causing electrical power surges, making extra big auroras, and interfering with radio wave transmissions on Earth. People who are ham radio operators, the high frequency AM, that can bounce their radio waves off the ionosphere and back down and off it and back down again to talk to people all around the Earth. When you get these huge magnetic storms, it interferes with their frequencies as well. Fun fact, the short waves of AM radio do bounce off the ionosphere and come back down and bounce off again. So you can pick up stations like 850 AM KOA out of Denver, Colorado. At nighttime when the other AMs go off, it's because it bounces it off the ionosphere. Try it sometime. Listen to Denver Nuggets game. Oh wait, not right now with the Corona thing. So there we go. Another picture of the Corona magnetic storms. Okay, last but not least, I want to leave you with a practice question. So scientists have discovered that Earth loses about 180 liters a minute of water to space, just at the poles, where it rises up and escapes out of the North and South poles. Kind of scary thought, but this has been going on for the last few thousand years or more. So let's say a typical 1 acre farm pond contains about 1,235,000 liters of water. How long would it take for the Earth to lose as much water as is needed to fill that typical farm pond? Well, let's do the math. 180 liters a minute times 60 minutes an hour is 10,800 liters per hour. Holy Hannibal Lecter's Batman, that's a lot of water. At 10,000 liters an hour times a day, 24 hours a day, you get 259,000 liters. That's a lot of water every day lost to the poles. Now the farm pond divided by that many liters a day, it takes only 4.5 days, almost 5 days, to lose a farm pond of water. Dang shooby-doo. So, how long would it take to lose as much water as is in the Lake of the Ozarks? Okay, that's a pretty big lake. Most of you been there? There's 617 billion gallons of water, or 2.335 trillion liters of water. Convert gallons to liters. Okay, so you take that many liters divided by how much we figured out we lose per day, 259,000 liters a day in the lake, divided by that equals about 9 million days. Yeah, that's a lot of days. It would take 24,680 years to lose as much water as contained in the Lake of the Ozarks. So, if you, which equates to, yeah, I did the math for Lake Erie just for fun. 5 million years to drain Lake Erie. Of course, that's one of our big lakes here in North America, but just in case you're interested. Just a fun thing. And I am done with the flip notes. In lieu of a test, you will take the Socrative, go to www.socrative.com, classroom dinner, take the quiz, and keep doing it until you get 90%. Make sure you put your last name and first name on there so I can give credit where credit is due. Once you get 90%, that means you've mastered the material. And do that by noon on Sunday. We'll move on from there with the life cycle of stars next.